Good day, everyone. My name is Chantal Janse van Vuren, and I'm currently a PhD student at the University of Stellenbosch in South Africa. Today I will be presenting the paper titled A Self-Organizing Map Approach for the Time of Use Feature-Based Wind Resource Clustering. This paper is being presented at the International Renewable Energy Congress 2020. Introducing the paper authors, we have Professor Hendrik Johan Vermeulen, Dr. Matthew Kroch, and myself, Chantal Yvonne Janse van Vuren. Now let's look at a quick overview of this paper. We start with an introduction and then define the resource datasets and focus areas. We also have a look at the Megaflex tariff structure for South Africa and the associated statistical input parameters. We then use these statistical input parameters as the self-organizing map clusters input, creating clustered wind resource maps. We round off with a cluster methodology comparison, finishing with the discussions and conclusions. In this paper, we focus on the South African region, where South Africa has an energy supply which is dominated by coal. However, the concept in this paper can be applied worldwide since there is a growing penetration of renewable energy, especially wind energy. This increases the operational challenges induced by the variable nature of these sources. These challenges include increased use of peaking generation and ancillary services, as well as increased ramping of conventional power plants. Now, the variability and uncertainty of the renewable resource furthermore complicates the short-term forecasting of the associated generation profiles. Now, the adverse effects associated with the variable nature of wind and solar voltaic generation can, however, be mitigated by optimizing the geographic siting of these resources. This work explores the application of a self-organizing map approach for the clustering of temporospatial wind speed profiles with a view to derive clustered resource maps for the subsequent use in a siting optimization study. Unlike the most common approach, which clusters the actual temporal profiles, the clustering is performed using feature vectors defined in terms of the statistical parameters of the temporospatial wind speed profiles, and these profiles are defined for individual time of use periods. Let's have a look at the resource datasets and focus areas. The proposed clustering approach is implemented for the wind resource datasets associated with the South African renewable energy development zones. Now here we can see in the figure that these zones represent 8 distinct geographic regions within South Africa, and these zones have been demarcated for future development of renewable energy based on criteria such as environmental, economic, and socio-economic factors. The proposed self-organizing maps clustering methodology is implemented for a numerical wind resource dataset using a weather research forecasting model. Now this wind atlas dataset has a spatial resolution of 5 by 5 kilometers, a temporal resolution of 15 minutes, and a temporal coverage spanning the calendar years from 2009 to 2013. As you can imagine, for each one of these data points lying within the 8 renewable energy development zones, there is a vast amount of temporal data. Now, optimal siting studies for large geographic areas with diverse climatic conditions in practice make use of large temporospatial datasets. Wind and solar PV datasets with high temporospatial resolutions are readily available, but the practical use of these large datasets for siting optimization studies requires considerable computational power. Now, this computational burden can, however, be reduced by the application of data reduction techniques such as clustering. And clustering in this context entails indexing of sites with similar temporospatial and statistical profiles into representative groups with minimal loss of information. Now, the aim in this research paper is to convert this temporal dataset to a statistical dataset defined in terms of the time of use tariff structure within South Africa. So let's have a closer look at the South African Megaflex tariff structure. Now, the time of use cost of energy, irrespective of whether it reflects the cost in a sophisticated market where real-time pricing and marketing applies, or a more rigorous environment where a set of time of use tariffs apply, reflect the cost and income of generation and transmission of electrical energy. So therefore, the yield during the individual time of use periods represent useful information in analyzing energy yield from a variable, non-dispatchable renewable energy resource. Now, the South African power utility, Eskom, implements a fixed time of use tariff structure for resellers and large customers connected at the transmission level. This time of use tariff structure incorporates two distinct demand seasons. And these demand seasons are the high demand season, ranging from the 1st of June to the 31st of August, and the low demand season, ranging from the 1st of September to the 31st of May. Now, this tariff structure furthermore incorporates three categories of daily time of use periods, namely the off-peak period, shown in green, the standard period, shown in yellow, and the peak period, shown in red. Now, these two tariff profiles for the low demand and high demand season will be the basis of the statistical input layer for the clustering of this wind resource dataset. Let's define the statistical input parameters. So the first table summarizes the weekly time of use periods defined by the Megaflex time of use tariff structure. Now, as we can see, these 7 periods in the low demand season and the 6 periods in the high demand season represents the green, yellow, and red blocks shown in the previous slide. Now, the feature vector defined for the input layer of the self-organizing maps consists of statistical parameters for the wind speed distributions associated with the various Megaflex time of use periods, and this is defined in the first table as we saw. Now, the features calculated for each time of use period includes the mean wind speed and the standard deviation. Within the 8 renewable energy development zones, there is 3,173 points represented by temporal wind speeds. These temporal wind speeds span a 5-year period and can be quite large. Now, what we do here is translate these temporal profiles into statistical input parameters, where we decrease the temporal line to simply 26 statistical features for each of the 3,173 sites. The 26 statistical features consist of the standard deviation and mean wind speeds for each of the low demand season's time of use periods, as well as the wind speed and standard deviation for each of the high demand season time of use periods. Now, what we notice when we look at the second table is that the second table summarizes the normalized cost of energy for the Megaflex time of use tariff system. This table shows the cost of electricity is significantly higher for the peak time of use periods compared to the standard and off-peak periods. It also shows that specifically for peak periods, the cost is substantially higher for the high demand season compared to the low demand season. So what we're essentially doing when we reduce each of the temporal lines for each of the low demand and high demand time of use periods is reduce these varying temporal profiles to two statistically defined features. This creates an equal weighting for each of the time of use periods. Now, as we saw with the previous time of use tariff structure, the off-peak period, which in this case is not as important to us for siting purposes, is defined over a higher temporal range, whereas the high demand season, morning peak and evening peak periods are defined over a much shorter time interval. Now, this is not ideal when looking at clustering purposes, since the clustering methodology will favor the periods which have a longer temporal range. Therefore, what we've done here by creating a statistical input parameter for each of these time of use periods is we allow the peak periods to have the same influence on the temporal line as the off-peak periods, even though their temporal influence on the site is a lot lower. This will output clusters which are better defined in terms of the time of use tariff structure, which in essence favors the generation profile representative of yield importance. So now that we've defined our statistical input parameters, let's have a look at the results of the self-organizing map clusters. So first we see that the optimal number of clusters for partitioning the target region for the purposes of this study is defined using the elbow method. Now this can be seen in the first figure. This figure shows a plot of the average intercluster sum of squares versus the increasing number of clusters. Now, using visual inspection, this suggests that 6 is an optimal number of clusters for this dataset. This is indicated by the inflection point where the change in intracluster sum of squares with an increased number of clusters becomes marginal. Now, looking at the next figure, we see that the self-organizing map algorithm takes an n-dimensional dataset and reduces it to clusters in a 2-dimensional space. The relationship between the neurons and the feature inputs are reduced to Euclidean distances of scalar values. This allows visualization as a 2-dimensional plot. The SOM is implemented for 6 clusters, which translates to a map with a grid dimension of 2 times 3 and 6 neurons in the output layer of the ANN model. Now the small grey dots represent the relationships between the feature of input vectors and the corresponding weight vectors with the neurons. The neuron weight vectors define the cluster space, and the red lines indicate the links between the neighboring neurons. Using visual inspection, we see that the clusters are well separated. Now let's analyze the clusters. The first figure shows the probability density distribution of the wind speeds of all of the coordinates contained in each of the clusters. Now the probability density distribution of the unclustered wind speeds is given for comparison, and this is the dotted black line. So the results show that the individual clusters exhibit distinct variations in the associated wind speed probability density functions. And this indicates that grouping with defining characteristics have been partitioned within the dataset. In the next figure, we see the mean and standard deviations of the wind speed profiles associated with the clustered as well as the unclustered profiles. Here we can see that cluster 2 and cluster 5 exhibit similar means but different standard deviations. We also see that cluster 1 and 2 exhibit similar standard deviations but different means. Now this indicates that the clusters are distinct with reference to the mean and variable features of the constituent temporospatial wind speed profiles. Now finally we get to the wind resource maps. Here we see, in the first diagram, a color-coded map of the locations of the clustered wind speed profiles. Now the individual clusters clearly represent well-defined geographic regions. And in view of the fact that the clustering is performed based on the statistical properties of the temporospatial wind speed profiles for the individual time of use periods, the map represents a useful resource for citing wind generation capacity, such that the aggregated power generation profile is optimized in terms of these time of use grid requirements. In the second figure, we see the locations of the clustered wind speed profiles on an elevation map. Now these clusters exhibit a high degree of correlation with the topographical features, where we see that in cluster 2, for example, a high degree of correlation with the elevation patterns of an inland and mountainous area is seen. We also see that in clusters 4 and 5, there is good correlation with low elevation within the coastal plain. Now overall, we see that there is a high degree of correlation between these individual clusters, as well as the associated geographical areas and the topographical features. Now here we have a quick look at the cluster methodology result comparison, and we compare the clustered maps obtained with the self-organizing maps approach with the results obtained for the popular k-means and k-medoids algorithms. Now, overall, the results show fair correlation, and the self-organizing maps and k-means results correlate well for the lower and coastal levels. Now these results provide a visual validation tool for comparing the performance of the self-organizing maps approach with the k-means and the k-medoids methods for clustering wind speed profiles. And this is especially in the view of the fact that the k-means and the k-medoids algorithms are used regularly in this context. Now coming to a close, we see that the self-organizing maps approach is applied to cluster a temporospatial wind resource datasets based on the time of use statistical features of the associated wind speed profiles. Now these statistical features are the mean and standard deviations of the wind speed, and the clusters obtained exhibit a high degree of correlation with the geographic location and the associated topographical features. The translation of the temporal profiles to the statistical features also aid in providing a method which highly reduces the dimensionality of the resource dataset, lightening the computational burden of the resulting clustered algorithm output. Now the resulting clustered resource maps are a value for citing wind generation capacity such that the aggregated power generation profile is optimized in terms of time of use grid support. Thank you.